everybody. I hope everyone's having a wonderful day. So, I'm going to be picking up from more discussion involving DFS. So remember, in depth first search, what was the strategy we used? Well, what we did was we started off at some starting vertex, and we tried to determine all the edges and vertices reachable from that starting vertex. So, I'm going to show you a variety of different ways that we can use DFS with simple modifications to solve various other problems. And then after that, we're going to talk about another standard type of graph traversal called a breadth first search. So I thought it would be natural to start off with this one first. It's pathfinding. So imagine I have a graph where I have some vertex I'm at, and I would like to get to some other vertex, which is my destination. So I want to get from S to T. We call this typically an ST path. So my goal is to find such a path and tell you either is there or isn't there, and possibly what the path actually is. So we're going to walk, before I show you what the algorithm is, I'm going to walk through DFS, and I'm just going to keep around one extra thing, just to illustrate things. So first, I'm not going to really care much about labeling edges. That's not going to be terribly relevant for us here. What I'm going to do is I'm going to hang around with an extra stack here that is not the call stack. The call stack's over there. We're going to start off at S here, which is just vertex A. I'm going to keep around this stack P, which can be some local or global variable. It's something that I'm keeping around for keeping track of the path that we're going to find. So you're going to see how I'm going to use this as I'm trying to find them. You're going to see that these two are going to be kind of related to one another. So let's start off with what we would normally do. So what would we do in DFS? Well, I would mark the vertex, right? Now what I'm going to do is I'm going to push A into the stack P, and then I'm going to look at all of my incident edges and see if I have any endpoints that I haven't found yet. Well, I can discover B by a discovery edge here. I'm not going to worry about labeling these because you're going to see it's not going to be very relevant for us here. The point is now I have this one, so I can call DFS on vertex B, so the call stack now has B on it. What's the first thing I do? I'm going to mark it, and then I'm going to then push B onto this stack here. Now, I need to do the same thing I did before. I consider incident edges. Let's say I consider D first. Just out of chance, this happened to be the one I encountered first. It could have been this one, it doesn't matter. So I'm going to go to D, so it means that I call DFS, DFS, I'm getting ahead of myself. I'm going to call DFS on D, where I go and mark it. I put it on the stack, D, and then what do? I go through all the incident edges, right? But do I have any that I have not yet marked? Well, it's just B, but B's already been marked, right? So I don't really care about that. So do I have anything else I need to do at D? Well, I've checked all my incident edges. Now, what P is going to contain is the path that we're going to find. So naturally, D is not going to be in here, so I better pop D off, and naturally I'm going to finish execution with D. So DFS with D is finished. Then I go back to D. Remember, think of the string. I pull it back so I don't get lost. So I go back to D. Then I consider another incident edge of an unmarked vertex, which is C. So I go to C. I mark it. And then I'm going to push C onto the stack, P. And then I consider incident edges again. I only have one that isn't marked, right? So what am I going to do? I'm going to go call DFS on E. So here's E right here. So now I'm calling DFS on E. Since I marked it, I'm going to push E onto the stack P. Then what am I going to do? Well, E is T, right? So do I have to consider any incident edges? No, right? I'm already there. I'm already at the destination. So what am I going to do? Well, I'm going to return true from this, saying, hey, look, I found it. So what does that mean? I'm going to return true, pass it along now to C. Well, I have nothing else really to explore, but keep in mind, I've returned true, saying, hey, look, I found it. So C shouldn't do anything else. And now, okay, well, now back to B. B got a true, so that means I found it. And naturally, A got one, and I returned the result true. So that's just me executing DFS, where I've just ignored labeling the edges. So it's a very slight modification I made. However, I have this stack P. Do you see the ST path? Do you see it? Where is it? If I'm starting at S and I want to go to T, where is it? Just look at this stack here. Read it like this. A, B, C, E. A, B, C, E. So if you read it from top to bottom, if you just pop them off, you'll get this path backwards. If you want it from S to T, you're just simply going to read it from back to front, right? So you see how we can just simply adapt the DFS to do this? So what I'm going to do is I'm going to write down the pseudocode for this. And the great thing is because we've done the delicate analysis, you can see very clearly that this is really not going to change anything involving the time complexities, right? I just introduced the stack, and we know that pushing and popping takes cost and time in a reasonable implementation of a stack, right? So what do I do in DFS again? I mark the vertex that I'm at. Now, Note that I don't have a U here, I have an S and a T, so I'm going to mark S as if that was my starting vertex. And then I'm going to push into my stack. Remember, after I mark it, I push it into the stack. So I'm going to push S in there. And then I check. Is S equal to T? If it is, then what did I do? I return true. I return true. Otherwise, what did I do? I just kind of do what I normally do in DFS. So I go for each. So I need to go through all my incident edges. For each edge, S, U. So U is the other endpoint for which SU is an incident edge on S. You're going to do the following. So if I know that U is not marked, remember, we only care about the ones that aren't marked right now. So if U is not marked, then what? What do we do? Well, I better call path find, right? So I'm going to call path find on what? So the way I want you to look at this is as I find more and more of the path as I discover, I'm asking actually a slightly tweaked question, aren't I? I'm actually asking is when I get to B, is there a path from B to E? When I'm at D, am I looking for a path from D to E? What I want to do is I want to ask this question from over there. And now keep in mind when I say this, I'm talking about from points for which I've yet to discover. So obviously when I answer D, the answer is of course no, right? Because I've explored every other part that is incident on it. Thus there's no discovery of a path. So I go back to B, right? So what do? I'm just going to go if path find. So I'm going to recursively call on path find. And I'm just going to go, I put U in right there and just put it with T. If this is equal to true, then we're going to return true. Right? So if I find this path, then I better return true. That's what I did when I cascaded up, right? As soon as I found it, I worked my way back all the way to S. Now, what do I do if I check all my incident edges? All the incident edges on S. What do? I better pop the stack because I've considered all possibilities. So I'm going to go P dot pop. I'm going to call pop, and because I had the pop, that means I was unsuccessful from that vertex to find a path that has yet to be explored. So I better return false here. So I return false, and that concludes the else block. And that's it. So you can use this to compute an ST path. So this is one trivial modification we can make to DFS. So that is the first one I wanted to show you. So hopefully you find this kind of interesting. I should also remark that one thing I really want you to illustrate, just because I've drawn you two stacks, is you see the behavior of this stack is quite similar to that one. Well, because DFS is naturally working with a stack to explore the graph. I want you to notice that, because this will become relevant later. So if you really don't like this recursion, you can always use your own stack. Hey, the next thing I want to talk about is the concept of detecting a cycle. Let's talk about cycle detection. So I showed you how you can find a path, an ST path. I've shown you DFS, but I want to come back to something we talked about last day. There are two kinds of edges that I've labeled. discovery edges and back edges. So just to illustrate DFS again, so I'm just going to have just a simple graph that just looks like this. So when I execute DFS, where U is A, the starting vertex, what happens? Well, I might potentially, I mark this, then I consider my incident edges. I then find one here. I label this as a discovery edge. And then I go to B. What do? I consider my incident edges. I find one right here. I label as a discovery edge. Then I mark C. Then I get a discovery edge. Now, I want to remind you, what's a cycle? Well, it's a path for which the start and the end of the path are exactly the same. Now, I want you to notice that when I reach D, I mark this. And what does this edge get labeled as? What does it get labeled as? Is this a discovery edge? No, this is a back edge. So this would be labeled as a back edge. So it gets labeled as a back edge. Why do we label it as a back edge? It's because in DFS, if we already marked a vertex of one of our incident edges, we know that we indeed visited there already once in the past. So what does that mean? That means that there exists a cycle. Does everybody see that? Why? Because there had to have been some way I got all the way here, and then I rediscovered A from this vertex. That implies there's an existing path that got me here to get me over to A again. But we obviously don't go that way. We just kind of work our way back around. So how do we detect a cycle? How do we know a cycle exists? So I'm going to say observe that if the DFS labels an edge as a back edge, then there must be at least one cycle. Did everybody see that? So you can specialize DFS to detect cycles. So you can find a cycle, compute a cycle. The key thing is it's just a cycle. So it's not very hard to see how you can modify this to get a cycle detection algorithm. So just see the notes for the pseudocode for this. See the notes for the pseudocode for this. You'll see it's very much a trivial modification. This time I care about the difference between a discovery edge and a back edge. However, remember I still have to mark the vertices because I need to make sure I make progress in my search. Otherwise, I might find myself rediscovering vertices and never really terminating, okay? Although technically you could modify it so that if you label all the incident edges, you never go past a certain kind of edge. Obviously, we only care about the ones that are not labeled, right? So you just have to be careful. Okay, so that's another way you can modify DFS. So let's talk about counting vertices. How can you count vertices in a graph using DFS? So what's a neat property that DFS has? When I did this exploration, when I did my pathfinding, what was the potential possibility? I could have visited the entire graph, but did I visit vertices more than once? When I mean visit, I mean that I had a record on my stack. Did I at all have more than one of the same? No. What happened was I marked a vertex only once. So maybe there might be some cleanup at the beginning of the algorithm to tidy up the graph, make sure nothing is marked, or maybe nothing is labeled. However, when I call DFS on a starting vertex, if it's reachable, it will mark it, but it only marks it once. So I want you to observe. So I want to say, notice that we visit each vertex once. When is that? That's when you discover it, right? We visit each vertex once when we mark it. So we're going to use this fact to count vertices. So say if you wanted to know how many vertices are in the graph and you don't really know a whole lot about the graph, now obviously if you constructed the graph yourself, you'll probably know how many vertices there are. But imagine just for the sake of argument, you're just given an arbitrary graph, you don't know the topology of the graph other than perhaps it might be connected. So what would you do? Well, you could attempt to, so obviously there's a lot of workarounds you can do. I'm just going to propose that maybe if you have no access to the entire graph, you might need to do something like this and crawl through the graph. Which is possible, and it happens in settings like distributed settings where you might not have access to the entire graph, or accessing the entire graph is very expensive. Okay, so let's talk about the pseudocode for this one. Let's make some small modifications. The big thing I want you to realize is that we're not making any major changes to the algorithms. They still have the same time complexities. So when we talk about pathfinding, everything I said about adjacency matrices and their representations is just as true as for these other cases here, just like for the adjacency list representation. So we have count vert. So I'm going to call this count vert, and I get some starting vertex. We'll say vertex u in V of graph V. And the output is just going to be the number of vertices. The number of vertices reachable from U. Remember, the graph might not necessarily be connected, okay? So what was the first thing we do in DFS again? We mark the vertex. So I'm going to mark U, and then I'm going to do my count. I'm going to count. So I'm going to start off with a counter, and this counter is going to be increased as this occurs. So I recommend just pulling out a test graph and try running through the pseudocode by yourself on your spare time. So what was the next thing I do in DFS? Well, I may need to go through all the incident edges, right? So count purpose is to keep track of how many vertices I have encountered. So for each UV, we're going to do the following. So if V is not marked, this is going to be another case where I'm not going to care so much about if the edges are labeled or not. But if you want to be more particular, the big thing I want you to take away is that you can modify the structure of DFS. If you want to have it where the discovery edges and the back edges, the point is that you could make these small modifications. Here we care about the counting of the vertices. We don't really care about those edges. Remember, we're just trying to keep it simple. So if V is not marked, remember this is an edge that is incident on U, where V is the other endpoint. What am I going to do? I'm going to update count to be the recursive call of count vert on V plus count. So I'm just going to increase the count variable by the result of count vert. So I'll naturally just look over all my incident edges. And then I'm just going to return count. Simple. Is that nice? So using this, that's what you need to count all the vertices in a graph that are, well, assuming it's connected, right? If it isn't, then it's just going to be the ones reachable from you. So I want you to observe something. So I'm going to do one more case of DFS with you. And I want you to observe a very important property that I'm going to do here with you. So I'm going to draw out a graph. Switch markers. Okay, so here's a graph. Now I'm going to perform DFS on this graph starting from A. So imagine U is right here. What do? Well, I mark this vertex, then I consider my incident edges. Now suppose I go and I find the edge that connects me to C. So the vertex C is adjacent to A. And just to make it a little easier for myself, the discovery edge is going to be indicated by an arrow like this. And I visit C, so I mark that. Which incident edge isn't visited yet? It's the one that goes to D, right? So I label this as a discovery edge. I should remark that these discovery edges are sometimes called forward edges. So this is a discovery or forward edge. This is in contrast with a back edge, right? So it's sometimes called a forward edge. Like as you're going forward, like I'm walking forward. The intention of this will become very clear why you might consider using this term forward as opposed to discovery, but either one, they're synonyms. Okay, now if I'm at D, what do? Well, I'm going to go to B next, and then I'm going to mark B. Now, what is this? This is a back edge, right? So I'm going to use some dashed lines to indicate that's a back edge. And then what am I going to do? Well, I've considered all these, so I back up. Remember, I roll back my string so I don't get lost in this labyrinth. And then what I'm going to do is I'm going to go to my next incident edge, which is this one. And so that is a forward edge or discovery edge. I mark this. And notice my only one is just this one, which will end up being a back edge. So notice that when I'm done this, so notice this is done, then that's done, then this is done, this is done. So I end up with this. Now, the neat thing about this is that what does this look like if I ignore the dashed edges, the back edges? So what if I ignore these back edges? To make it a little bit more apparent, I'm going to use a red marker. So what do we call that in graph theory? What is that? That's a tree. So the forward edges, or discovery edges, form a tree. So discovery, or forward edges, form a tree. And what is this called? This is called a DFS tree. I might naturally ask, why do you get a tree? It's because, remember, I don't include the back edges. The back edges would be what would cause cycles. Remember, we established a back edge determines the existence of a cycle. So if I ignore all the back edges, there's no way there's going to be a cycle, right? So we end up with a DFS tree. So I just want to point out that if G, the graph, is connected, the DFS tree is a spanning subgraph. A spanning subgraph of G, which I'll define in a moment. In particular, a spanning tree. A spanning tree. We'll talk about spanning trees maybe next time. in more detail. So a spanning subgraph, just for clarity, a spanning subgraph is and I'm going to say that it's not necessarily connected. So not necessarily connected. It doesn't have to be connected. Not necessarily connected subgraph H that contains all the vertices of G. So of the graph G. So that's what a spanning subgraph is. So this DFS tree, if the graph is connected, is a spanning subgraph. So note, obviously, if you run DFS over the entire graph, you'll end up with a spanning. So if this is just a spanning tree, assuming it's connected, if it's not connected, what do we have a name for a whole bunch of trees? It was called a spanning forest, right? So you'd end up with a spanning forest. But I'm just going to define a spanning tree here. We'll need that later. So a spanning tree, as naturally, it's a spanning subgraph. A spanning subgraph H, that is a tree, right? Okay. So, believe it or not, that's all I have to say about DFS. So DFS is highly applicable to many types of graph problems that involve traversing over the entire graph. It's very natural and simple. So we're going to talk about another graph traversal. So I'm going to start you off with a little bit of discussion, but a new title here. We're going to call this breadth first search. Or BFS. Now, before I tell you what BFS is, I want to draw on an interesting analogy in terms of exploration. So, in DFS, we went depth-wise into the graph. And I want you to think back to when we were trying to find a path. What did we do? We kind of just went head in and we just went as deep, far as possible in the hope that we would find it. We might hit a dead end, but we would back up and hopefully find it if it exists, right? I want to draw it in contrast. So let's say kind of a depth-wise approach to doing things. I want to take a different approach. So instead of just diving, I want to think about what would happen if I were being a little bit more careful and say I was excavating and I want to find the path, but I don't want to just kind of go depth first into, say, a jungle. So I want to take you and make you imagine that you're in some jungle. And out in the jungle, we're looking for this special temple. So here's my temple. It's a lovely picture. This ancient temple. And I just want to see if I can find it, because I hear it's really awesome. It's called the Lost Temple of Awesome. So I want to locate this, but this is in the deep jungle, and there's a lot of risk for me just going into the middle of nowhere. I might get attacked by some wild animal, maybe a jaguar or something. And say there's just some paths that I can take. And then maybe there's some other path that kind of just goes on a schism way out this way. And say I start there at the black dot. And I want to find the lost Temple of Awesome. This is a big jungle. And I want to find it. I really like exploring sometimes. So what's one way I can do this? I can first, if I was in a rush, I might just like run right into the forest, into this jungle and be like, hey, I'm going to go find it. However, it's really hard for me to tell where to go because the trees are really tall. So I might just like go this way, all the way along this path and kind of veer off in this corner. Because remember, I don't know where this temple is. I can't see it. This is a very deep jungle. I might go all the way over here, then whoop, there's a jaguar. Not fun. That is not fun at all. That's where you lose your extra life, okay? So, what is another approach we can use? So that's a depth-wise approach to get me over here. What's a breadth-wise way I can do things? Now what I'm going to do is instead, I'm going to take, say, a proximal distance, and I'm going to investigate all paths from my starting point from this distance and explore the paths that I have so far. If I'm a little bit more careful, maybe I can avoid going into that deep, long path that might get me in not a fun place with the jaguar, okay? So, if I keep investigating, keep in mind, I'm not exploring this part. I'm only exploring the path here as I'm going across and doing this breadth-wise search. You'll notice that the distance I travel is only in some incremental steps. These should all be about equally spaced. The point is that if I take a breadth-wise approach, I could avoid this really long veering path. For example, I might eventually discover this fork and see the temple right there. Be like, hey, here's me. I wear a cool hat. There's me wearing a cool hat. And I found it. So the idea is we're going to take a breadth-wise approach by making incremental improvements towards possibly the entire graph's exploration. So that's kind of our goal. So DFS you can think of as depth-wise. So DFS is breadth-wise. So another point I want to bring up is earlier I talked about the relationship between a stack and DFS. BFS's relationship in relation to DFS, the BFS, it uses a queue. So instead of using a stack, we're going to use a queue. And you're going to find that what we're going to do is very similar. The only difference really, well, the major difference is just going to be we're going to use a queue. This queue will emulate this behavior, that we're going to go level by level through this exploration process incrementally. And that's going to be what's going to happen. So, let's talk about BFS. So, I'm going to write down BFS, and then we're going to do an example, and then we'll talk a little bit more about BFS. So, the input is a vertex U and V of a graph E, and BFS is going to take in a starting vertex U, just like before. This is a BFS traversal of J starting at U. So what we're going to do is we're going to start off with an empty Q. I'm going to call it Q. So I'm going to say I'm going to initialize an empty Q. And then I'm going to NQ, or enter, the starting vertex. Now, just like DFS, I'm going to mark that vertex. So whenever I NQ, I'm going to mark the vertex. So now I'm going to have a while loop. So I'm going to say while Q is not empty. Because if it was empty, that means we would have naturally explored everything that's reachable from U. That's at least kind of what we have to have in mind. So what's the first thing I'm going to do? I'm going to DQ from the Q so that I can take that one out and look at all of its incident edges, just like what we do with DFS. Remember, the big difference here is just we're going to use a queue instead of a stack. Does everybody see that? So what do we do? Once we do this, we're going to, now just for the sake of completeness, I'm just going to put a little subroutine here. I'm just going to call process V. So this would be where you would do your processing. So this would just be, this is where you would do something. I'm not going to really say a whole lot what process does. The point is it's just some sort of black box that you can use in your algorithm implementation if you find it interesting. So what do we do every other time? We're going to go through every one of the incident edges. So for every edge, VW, so I'm going to get all the edges incident on V. This other endpoint I'm going to call W. What did we do? We just checked if the edge wasn't labeled, right? If VW is not labeled, then we check if it's marked, right? If W is marked, then we're going to label this edge. Now, I'm not going to label it as a back edge. Instead, I'm going to label it as a cross edge. I'll talk more about what a cross edge means in a bit. It's called a cross edge. It has a name for a reason. Otherwise, what do we do? We're going to label a discovery edge. We're going to label VW as discovery edge. And then I'm going to NQ it into my queue. Q.NQ. I'm going to NQ W, and then what did I say earlier? I'm always going to mark it when I NQ it in. So then I'm just going to mark. It's kind of getting a little small down here, but below the NQ, I'm going to mark W. I'm going to mark W, and then I'll just have all my closed parentheses. All my closed curly braces all below here. I kind of run out of space, but the indenting should all be natural for you. So this is what BFS is. Just for the sake of time, I'm not going to talk about the analysis for BFS. I have it in the notes, but it's the same time complexities you would have in the other case. So for an adjacency matrix, this will take big O of n squared. For an adjacency list representation, you should expect the big O of n plus n, just like what we had for DFS. So I'll let you think about the analysis for this. It's actually quite similar. The only difference is just that we have this Q kicking around, and the Q plays a slightly different role for the adjacency matrix analysis. Okay, everybody, so here's an example right here. So I have an input graph here. Now, I'm marking two vertices, an S and a T. You might recall these from when I was doing the pathfinding earlier on. I'm going to show you two things at the same time. I'm going to show you the example with BFS, and I'm also going to show you how you can find a path using BFS. So I made a slight modification to the pseudocode here to retain a parent reference in reference to a tree structure. Hence, kind of like a DFS tree, we're going to find that a BFS can also produce a tree. So I'm going to have the starting vertex's parent be set to null. So each one of the vertices is going to have an attribute called its parent. It's going to be null. And whenever I mark a vertex, I'm going to assign its parent to be the other endpoint for which you're going into said vertex for an NQ. So for example, down below where I NQ W, I'm going to assign the parent of W to be V, where V is the opposing endpoint. So I want to show you two things at the same time. Why? Because I think you really can get this well. So I'm going to start off at S here. So I'm going to show you up to when I find T, but I'm going to go through the entire graph because I want to make sure you understand this. So I'm going to start off with 1. So it says I'm supposed to initialize Q. So I have initialized Q. I put in 1. What do? I mark 1. And then I assign the parent to be null. I've already done that for you. And then I'm going to go through my Q. Now, I have something in here, right? So I'm going to DQ1. Now, unlike DFS, we're going to go all the way in. We're going to do a breadthwise search from vertex 1. So what do? I DQ1. Now I have to go through all my incident edges, okay? So I'm going to have to go through this edge and that edge. I have to do both. So what do? I need to NQ2. Let's put in 2. Let's NQ2. What do I do with 2? Well, remember, I have to label this as a discovery edge. So I'm going to use wiggly lines to indicate a discovery edge. And when I NQ it, I mark it. And set its parent, right? What's its parent? It's 1. Okay, now I have to do the other incident edge. Remember, this loop isn't finished yet. Remember, we're not going to go depthwise, and we're going breadthwise. So I discover this edge. I NQ in, what do I NQ? I NQ 8. And then I assign its parent to be 1. So now, what's next? What's next? I have to mark 8, right? Don't forget I have to mark 8. Don't forget I have to mark 8. Okay, now, have I considered all the edges incident on 1? Yes, I did. So what do? We go back up to the while loop. It's not empty, so I DQ 2. And now I go through all the incident edges of 2. Okay? But I want you to notice something. So I'm just going to kind of keep a little bit of a tally around as we make steps, kind of like my exploration in the deep jungle. So when I'm at 2 here, I consider all my incident edges. What about this one? What's this one do? Well, this is a cross edge because I've already marked that. So how about this one? This is, should I go with, let's go 3. Let's go 3 first. So I'm going to put that in. What do? What am I going to do? I'm going to NQ it. Going to NQ it. I assign its parent after I mark it. And its parent is 2, right? Now I want you to notice that when we finish this, it's going to almost look like we're making steps incrementally. The Q is going to enforce that we're going to go level by level through this. And I'm going to show you what I mean by level in a moment. So let's proceed. So am I done with 2? No. Remember, I still have this one here. So I discovery edge, I NQ it in, and then I mark it, and then I set its parent to be 2. Okay, now I've considered all the incident edges, right? So let's proceed. Now we got 8. So now let's look at vertex 8. Let's consider all of its incident edges. So this one's already marked, so we get a cross edge. So 8 to 4, this edge here is cross edge. This one is a discovery edge. So what do I do again? I NQ it, I mark it, and then I set its parent to be what I came from, 8. I'm running out of space, so I'm going to add some more here. I'm almost there though. Okay, I've considered all the edges incident on 8, so we're done with 8. Now next, I DQ3. Okay, I only have one incident edge. So I label this as discovery, or forward, however you'd like to say it. That's a 5. I mark it. I set its parent to be 3. And notice that this is in fact T. So if you are augmenting what I have here to be a pathfinding algorithm, what you do is you could just stop here and return back now what you have here. So you don't even need to continue anymore. To find the ST path, you just follow along the parent references from T. So you just hang on to T, then you can just get the path from following along through the parents with a loop. Does everybody see that? But I'm going to keep going because that's not all BFS does. So, okay, so now I have 5. I've marked it. I said it's parent. Okay, am I done with 3? Yeah, I'm done with 3. So let's go to 4. Okay, this is a cross edge because it's already marked. Okay, how about that one? Well, let's first do this one. This one hasn't been found yet, so I better do what? I NQ it. I mark it, and I set its parent to be 4. Okay, and let's say I have a cross edge here. Cross edge. Okay, so that's, now I've encountered all the vertices so far. 4 is done, 7's coming on. Okay, 7. Do I have any incident edges I have not yet labeled? This one here. That's a cross edge. There's nothing else to do here. How about 5? Any incident edges I need to consider? No. How about 6? Anything? No. The queue is now empty, and thus now I have finished BFS. And I end up with this right here. So this is my example of BFS. Do you see how you can get the ST path now? So you just follow the parents. So what you would do is you would just follow the parents up. So you just hang on to T. So you can either hang on to it, and since you know what T is when you're actually doing this, you can just get access parent and do it directly. Okay. So I want to talk a little bit about what I just said before. I'm just going to erase these. So I talked about this notion of levels. So when the algorithm begins, and I'm going to use a marker to do this, I want to draw on my explorations in the deep jungle. When I started off, I start off here, right? That's where I started off in the jungle. Next, what did I do? I considered 2 and 8, which are 1 step away from the starting point. I don't perceive any of these other ones until I've done this, right? So I'm going to refer to the starting one as level 0 or layer 0, L1 as level 1 or layer 1. Now, what did I do next? So next I considered 3, 4, and 7, right? So these ones are all a part of what level? They're all part of level 2. And how about these last 2? They're part of level 3. Now, the big thing I want you to observe here is how many edges does it take me to get from that vertex to the next level? How many edges does it take me to get from level 0 to level 1? Only 1 edge, right? To any vertex from level 0 to level 1 takes 1 edge. From level 0 to level 2, how many edges does it take? 1, 2. How many does it take if I want to get to level 3? 3 edges. Notice I incrementally expand my search breadth-wise. This gives you a very nice property I'm going to talk about in a moment. But can you see very clearly that the discovery edges form a tree just like before? So again, the discovery edges discovery edges form a tree called a BFS tree. Called the BFS tree. And you might naturally ask what the cross edges are about. So a cross edge VW is either on the same level or the next level as V. So what do I mean by that? Actually, or the next level. Let's make it a little bit of a shop here. On the same level as V or the next level. Notice the cross edges, they only cross at the same level or the next one, okay? So this is in contrast to a back edge, which indicates an ancestor. So you never go down in a DFS tree, you always go up. In BFS, the cross edges are on the same level or the next level down. So you can visualize if I took this tree and flipped it like this, you can see those cross edges, although they're not a part of the tree, they have a relationship with the levels of the tree. Okay? So I have one last thing I want to talk about before I summarize things for graph traversals. So I talked about these levels. So shortest paths. So a shortest ST path in a graph uses a least number of edges. So the smallest possible of edges to get from S to T. So remember, BFS explores level by level through the graph. And I said, each time you go one level, it's like I take my expansion and my search out one level, means I use one edge. When I go next, I use two edges. I use three edges. Can I do any less than that to get from S to T? No, because that would imply that there has to exist some layer or level between level 0 and level 2, for example, which simply couldn't be possible because it would have implied that this vertex had to have been adjacent to one on level 2, which simply did not happen in BFS, right? So I'm just going to say BFS computes shortest paths and its BFS tree is a shortest path tree. So it means if I wanted to get the shortest path from my starting vertex U to any other vertex, this would deliver me actually the shortest path from the starting vertex to any other vertex in this tree. It's a very powerful property. You would not want to use DFS to do this. DFS does not guarantee this property. So just in summary, I'm just going to give you a little table. So I'm going to give you an application and whether you can use DFS or BFS to do it. So we've talked about all of these. So if I want to compute a spanning forest or tree, or compute connected components, I could do that with both BFS and DFS. Pathfinding. We see that we can do both for DFS and BFS. How about computing or detecting a cycle? My marker's just dying, I apologize. So computing or detecting a cycle. You can do that with both of these. By the way, I'll let you think about where or how you detect a cycle with BFS. I'll let you think about that, okay? I'll give you a hint. It might be under a different name. Okay, and shortest path. So a shortest path. Can I do that with DFS? No. I can do it with DFS though. So anyways, this concludes my discussion on graph traversals. Now, one thing I want to point out is that the shortest paths that I get here, they rely on the number of edges. Now, at the beginning of our discussion of graphs, I talked about different lengths or costs or sizes on the edges. We're going to start talking about a couple problems that are on so-called weighted graphs next. So we'll talk about that soon. So thank you very much and have yourself a beautiful day.